Morenci, Arizona. August 1984, 1400 hours. The ambient air temperature on the floor of the Phelps Dodge open pit is 112 degrees Fahrenheit. A unit rig Lectra haul Mark 36, a massive diesel-electric haul truck, is beginning a 2.8-mile haul from the lower benches to the primary crusher. The grade is a continuous 6%. The truck is loaded with 170 tons of blasted porphyry copper. The operator in the cab is not looking at the speedometer. He is watching the ammeter, and he is listening to the pitch of the General Electric traction motors mounted in the rear wheel hubs. The Mark 36 was designed to move massive tonnage, but in the Sonoran Desert in midsummer, the engineering math begins to break down. The traction motors rely on forced air cooling. Grid blowers pull ambient air over the electrical components to dissipate the immense heat generated by moving 320 tons of combined vehicle and payload weight against gravity. But when the cooling air itself is 112 degrees, its thermal efficiency plummets. The temperature of the winding insulation inside the motors approaches its critical threshold rapidly. Inexperienced operators, focused only on the dispatch radio and the daily production target, hold the throttle wide open. They push the truck until the thermal warning lights illuminate or the motors physically degrade. The veteran operator behaves differently. He knows that operating at the absolute thermal edge in this specific climate destroys the winding insulation over the course of a single summer. He intentionally modulates the throttle, finding the exact amperage draw that the hot desert air can successfully cool. He deliberately sacrifices haul speed to protect the drive system. But the traction motors were only half of the thermal equation at Morenci. The physical temperature of the haul road itself was the real killer. The unit rig Lectra haul was officially rated for a 170-ton payload, but at Morenci in August, the actual loaded weight was heavily scrutinized and frequently restricted. This was not due to the structural limits of the steel frame or the horsepower of the 16-cylinder engine. It was dictated entirely by the ton-mile-per-hour rating of the massive rubber tires. A haul truck tire is an immense heat sink. When you place 320 tons of combined weight on 6 tires and roll them over crushed rock at 12 miles per hour for nearly 3 miles, the internal friction generates staggering temperatures. In the Arizona summer, the surface of the haul road itself frequently exceeded 140 degrees Fahrenheit. The tires could not shed their internal heat into the ground. Instead, the ground actively baked the tires. If an operator hauled a full payload at maximum speed along that route, the internal temperature of the rubber would rapidly exceed the vulcanization point. The tire would literally begin to melt from the inside out, causing the internal plies to separate. There was no dashboard warning light for ply separation in 1984. A failing tire bubbled internally as the structural rubber delaminated from the steel belts under extreme heat. The only sensor was the human being sitting in the cab. The veteran operator felt the impending failure as a slight, rhythmic vibration transferring through the heavy steering column or a subtle shimmy in the steel deck plate under his boots. It was a tactile warning that the tire was losing its structural integrity and was minutes away from exploding under 320 tons of pressure. When an experienced driver felt that rhythm, he immediately eased off the throttle. He brought the truck to a crawl, deliberately sacrificing his cycle time to prevent a $15,000 tire from shredding itself across the ramp. This action put the operator in direct conflict with the mine's dispatchers. The production target required the fleet to maintain specific speeds to keep the primary crusher fed. A truck crawling at 4 miles per hour backed up the entire haul road. The dispatcher, sitting in an air-conditioned tower looking at a stopwatch, only saw a slow truck. The operator, feeling the machine, knew he was saving a massive asset and preventing a blowout that could halt production for hours. This delicate thermal management could be completely undone before the truck ever left the loading bench. If the truck was loaded incorrectly, the heat buildup in the tires accelerated exponentially. The P&H 2800 electric mining shovel was a colossal machine, swinging a dipper capable of loading 40 to 50 tons of rock in a single pass. At Morenci, the interaction between the shovel and the truck was complicated by the severe desert dust that often choked visibility at the rock face. When the shovel runner could not clearly see the far rails of the truck bed, he risked dropping the payload off-center. If 170 tons of copper ore were loaded heavily toward the right side of the Mark 36, the mechanical math of the ton-mile-per-hour limit collapsed entirely. Instead of 320 tons distributed evenly across 6 tires, the right rear duals were suddenly forced to carry 60% of the total weight. On a long-haul route in 112-degree heat, an overloaded set of rear duals would exceed their thermal rating within the first mile. The extreme localized pressure created friction that the ambient air could not dissipate. New operators, focused rigidly on the dispatcher's radio, would take an asymmetrical load, put the truck in gear, and immediately push for the ramp. They operated on the assumption that a load was a load, and the manufacturer's rating meant the truck could handle it. The veteran operator knew that an off-center load in August was a guaranteed tire failure. He felt the uneven compression of the massive suspension struts before the truck moved an inch. The veteran operator refused to put the transmission in gear. Instead of pulling away with an asymmetrical load, he hit the air horn one long blast, followed by 2 short ones. This was the undocumented signal to the shovel operator that the load was fatally off-center. The dispatcher's voice would crackle over the radio, demanding the truck clear the bench to maintain the cycle time. The veteran driver simply ignored the radio. He understood that sitting idle for an extra 40 seconds, while the shovel operator used the back of the massive dipper door to physically push the copper ore toward the center line of the bed, was the only way to balance the suspension. Struts. By ensuring the rock was evenly distributed across all 6 tires, the operator brought the mechanical reality back into alignment with the rigid thermal rating. He traded a few seconds of cycle time on the flat pit floor to prevent a catastrophic tire failure 2 miles up the 6% grade. The production supervisors hated this standoff, but the veteran operators held their ground, prioritizing the survival of the iron over the stopwatch. When a new operator inevitably gave into dispatch pressure and drove an off-center load into the blazing Arizona heat, the failure was violent. The internal temperature of the rubber would surpass the vulcanization point. The steel belts delaminated, the tire bubbled aggressively, and the casing ruptured under 320 tons of combined pressure. The truck limped into the heavy tire shop at Morenci, crippled, riding low on a shredded rear dual. Replacing a massive earth mover tire in the 1980s was not a quick pit stop. It required specialized heavy tire handlers mounted on massive forklifts, immense hydraulic jacks, and hours of operational downtime. The maintenance foreman would examine the blown tire, tracing the failure directly to ply separation caused by asymmetrical weight and sustained heat. The financial cost was astronomical, not just the replacement of the expensive rubber, but the complete loss of that truck's copper production for the remainder of the shift. The manual reliance on operator instinct to balance the load and manage the ton-mile-per-hour rating was proving too variable against the relentless pressure of the production targets. The dispatch records only showed a truck that hadn't made its required daily tonnage. With human judgment failing under the stress of dispatch demands, the mine engineers had to attempt to systemically manage tire temperatures across the entire Morenci pit. The engineers could not change the Arizona sun, and they could not perfectly guarantee the fragmentation of every shovel load. So, they changed the routing. In the mid to late 1980s, the Morenci open pit became a critical proving ground for early computerized fleet dispatch systems. Instead of relying entirely on a human dispatcher with a clipboard and a radio, algorithms began calculating the accumulated heat of every truck in the fleet in real time. If the dispatch computer determined that a specific Mark 36 was running too hot after completing a grueling 6% climb out of the deep pit, it would deliberately alter the truck's next cycle. Instead of sending the truck back down into the deep, steep benches where the compressive forces were immense, the system would route it to a longer, flatter, upper bench to haul waste rock. This longer, flatter haul allowed the massive tires to continue rolling at a steady speed, which moved cooling air over the rubber without subjecting them to the severe flex and compressive heat of the steep grade. The computer was mathematically managing the heat through dynamic routing. It was an elegant engineering solution to a physical constraint. The trucks kept moving, but they were driving to cool down, not just to move ore. But prioritizing tire survival over direct ore routing created a massive logistical puzzle. When the computerized dispatch system sent a truck on a flat waste run merely to cool its rubber, that specific truck was temporarily removed from the critical copper ore cycle. To maintain the aggressive daily tonnage required by the Phelps Dodge concentrator, the mine suddenly needed more trucks on the haul roads just to compensate for the vehicles cooling off on secondary routes. This operational reality forced a massive capital expenditure. The fleet size had to expand. Consequently, the physical footprint of the Morenci pit widened. Haul roads were extended and modified to allow these complex, multi-tiered haul cycles to function safely without creating massive traffic jams. The machines were no longer just moving dirt from point A to point B. They were executing a carefully choreographed thermal rotation across the entire landscape. The integration of the computer solved the tire heat crisis, but it fundamentally altered the human element of the operation. The dispatch algorithms took total, centralized control over where every truck went, what material it hauled, and how fast it drove. The era of the autonomous operator making independent judgment calls based on the feel of the deck plate was ending. The veteran operators became passengers in their own cabs. The deep, physical knowledge of reading an off-center load, feathering the throttle to save a General Electric wheel motor, or feeling the subtle, rhythmic vibration of a failing tire was rendered functionally obsolete by the glowing dispatch screen. The system told them where to go, when to turn, and what speed to hold to maintain the perfect mathematical harmony of the pit. The algorithm had assumed the responsibility for the machine's survival. The experienced drivers, who had spent a decade mastering the delicate, dangerous balance between the payload and the punishing Morenci grades, found their judgment bypassed. As these older operators retired, they took that hyper-specific, undocumented sensory knowledge with them. The new operators entering the cabs in the late 1980s and early 1990s only knew how to follow the digital prompts. They drove the haul roads completely detached from the physical limits of the rubber and copper beneath them. The machine was protected by software, not by human instinct. The unspoken dialogue between the operator and the machine had been silenced. The last unit-rig Lectra Hall Mark 36s in active production service at Morenci were retired by the late 1990s. The industry had fully transitioned to massive 240-ton and 300-ton AC drive haulers. The surviving rigs were parked on the deadline, stripped for parts to keep other aging fleets alive, or eventually sold for scrap. What the maintenance records showed about how they had been operated, which drivers protected the tires, which ones cooked the wheel motors, what the veterans had done differently to survive the relentless Arizona heat went with the operators when they retired. Some of it was written down in informal shift logs. Most of it wasn't. The ramps at Morenci are still there. The desert heat is exactly the same. The trucks that run it now are massive, highly computerized, and know absolutely nothing about the heavy, calloused hands that once kept the fleet alive just by listening to the iron.